So this is very exciting. The biologists think it's great because they get to test their ideas on another system and validate that they have the right computational model for how the software works. And on robots, they can test things, they can change the software. You can't change any software very easily. And the roboticists, we like this because we get software that's been debugged, get it, for 150 million years, which is a very long lifetime. So it's great for everybody. So here's what I do. Here's my robots. You see most of these things work. The behavior license lets us know what the robots are doing. We didn't even bother to put screens on our robots because we have too many of them. You can't read the screens. There's a radio on the top that lets us get centralized command and control instructions to the robots. So that's what I was using when I was driving them around. There's a camera. I've only used that once. You see that in the video. They're looking for treasure in the room. The main system is their infrared communication and localization system. That lets them talk to their neighbors and share information and figure out where their neighbors are. There's an audio system that lets us know what they're doing. So you can kind of close your eyes and get a feeling of what the whole swarm is doing. Very useful. A bump skirt, so they know I got the face mask to the wall, and then 8 AA nickel cadmium batteries. So run the whole show. So that's too complicated to think about mathematically. So when I do my theory, I've got to simplify the robots to a circle with a little line. Again, I need to draw a lot of those because I think about lots of robots. Each robot has a range which can communicate with its neighbors, and that forms a local subnetwork. And if you take all the little local networks from all the robots, you end up with this mesh network. Now, once you have this mesh network, you can now do things with it. You can share information. Here's the source. The source sends information to these robots, to these ones, and these ones, and that information flows to the network. So you have a kind of broadcast flood. Once the information is out here, though, each robot now knows who it got their message from, and like you just saw on the stage, they can then navigate back and use that information. So robots can navigate from here to here to here to here, getting back to the source of information. That's how navigation works. Here's the information spreading on the swarm. You'll note that it is really, really slow. Why is it so slow? Because they can't talk very fast. Their infrared communication system is really pretty limited. And because their infrared communication is very slow, and they have to share their communication with all their neighbors, because if you're talking, I can't hear the person next to me talking, so they have to wait until the person talks, then they talk, and the other one talks, and yada, yada, yada. You end up with a message propagation speed that's really quite slow. I can outrun these messages on foot, and that can cause problems. So here they are navigating. So again, here's navigation. There's a blue robot here trying to get to this green robot down here. When nobody's moving, it works just fine because all the messages go out. They make their routing structure, and they can move themselves toward the source. However, if the robots are moving, it causes problems. We have a picture here. When the robots are moving, that causes problems. So on the left, you can see a static network, nice, pretty, odd numbers. Even numbers are blue, odd numbers are red. So we have 0, 1, 2, 3, and 4. That's how many times the message was relayed to get to them. Over here, though, as they move and shuffle, the network gets a little muddy. It gets a little confusing. And it's hard to see exactly which way to go. Turns out, as long as the network can update fast enough, the robots can get home safely. So let's put all this theory to work. Let's go do something useful. In this case, we're going to search for treasure in a building. The treasure in this case is a bright orange ball. Again, you can tell robots anything is treasure. They're not very smart. And the treasure is hidden over here on the left-hand side. And you're going to see 4 types of robots. Blue robots are going to be on the boundary between explored space and unexplored space. And they're going to ask the red robots to push them forward into unexplored space. White robots are guides. They're going to lead the humans to the treasure. And green robots have low batteries. They're going to go back and go charge. So off we go. This video is filmed about 8 times, I think. You can see the blue robots leading the way. And the treasure's over there by those tables. That's not very well hidden. The robots have already found it. When the lights go back off, you'll see some white robots. Those are guides. And they're going to lead us to the object of interest. And then green robots are going to go back and go charge. So you can see why it's important to have routing algorithms that always are able to update as the network is moving, as the network is always moving. Once we're done, we have to get them all back home. So here they are doing the cluster algorithm that you saw, where some robots stay put, and other ones move through them. And here they are all trying to get back home. And if you're paying attention, you notice that one little robot didn't quite make it home. We had 104 robots deployed that day. If one didn't get home, that's less than 1%. That's just fine. We had other problems, though. Turns out when you're 5 inches tall, the world is a very big place. So we tried a bunch of clever solutions to get them to detect when they were stuck and to do things and wiggle a little bit. And eventually we just gave up and walked around with duct tape. And that takes over all these registers, and that works way better. All right, so that's what I did. So the core of my research is on distributed algorithms and the software that lets lots of simple things work together to solve a problem. So let's do an example of that on stage. What I want you guys to do is I want to get 8 people, and let me get 8. Let's see if we have 8 high school students here. I think they would do. Let's get a gender balanced group of 8 high school students. Come on up. Everyone gets a card. Everyone gets a copy. We got 8 high school students? So, thank you, sorry about that. Okay, 8. Everyone have a calculator, everyone have a card? Okay, line up, right here. So what I want you all to do is compute the average of the number that you have on your card. But wait, I don't want you just to add them all up and divide by 8. That would be far too simple. What I want you to do is use a distributed algorithm. So what is that? So an algorithm is a procedure. It's what computer scientists spend all day long doing. And essentially it's like a recipe. So let's say you want to make cake. I like cake, chocolate cake is good. You start with a bunch of ingredients, and then you follow a procedure that says if you start with these ingredients and follow the procedure, you are guaranteed to get a cake. Well, depending on how well you follow the procedure. An algorithm is the exact same thing. You start with some data, you follow a procedure to operate on this data, and you are guaranteed to get something at the end. In this case, of what you guys are going to do, if you start with the data you have, which you had, because numbers, that's your data, and until you do what I ask you to do, you end up with the average. At least, so I say. A distributed algorithm is a recipe that runs in multiple chefs. So as opposed to having one chef for the cake, we have 8 chefs to cook our cake and run our software for us. Okay, so what I want you to do is I want you to do what's called linear average consensus. It looks way more complicated than this, and we'll look through it. I want everybody to take their numbers and hold them up so that everyone can see. The numbers are indeed not the same. So take your starting number and enter it onto your calculator. Yeah? Okay, all the cards come back to me. So now everybody find a partner and take the number on your calculator and take your partner's number and average those 2 numbers. So take their number, add your number, divide by 2. They take your number, their number, divide by 2. And when you're done, you should get the same answer. Yes. Okay? Take your new number, go find a different partner, and compute a new average with your new number and your new partner. And after you have a new number, keep on going. And it's okay if you partner with multiple people. It's okay if you have the same people multiple times. The only thing that you don't want to do is kick the robots. So keep on mixing it up and computing averages and have a great time. Okay, so while our computer is running, we have a little bit of free time. Are there any questions? No questions? Okay, here are the standard answers. There's a. I didn't know. You have to do something else, but I didn't ask any questions yet. All right. So typically, I'm kidding, guys. So typically, let me get. Who have their hand up for the question? Go ahead.
Why use the infrared interface? Because of the power, or just cheaper?
No, if you guys are really done, you can stop. Really. All right. So why use infrared interface? I use the infrared. I have infrared and radio. Radio does not transmit in nice straight lines. Radio is blocked by concrete, metal, me. I block the radio waves from the robots. So it's a very poor thing to test with in the lab. The infrared system gives me a nice clean circle around each robot, so I have a good estimate of who can talk to who just based on the distance between the two of them. So if I were outside in a field, radio would give me a nice clean, well, it would give me a cleaner sort of range around each robot. So using infrared in the lab is a good approximation, you could argue, for using radio out in the real world. The answer is that it's not, because radio still performs very badly in the real world. But at least it lets us do things in the lab that are reasonably accurate. It lets us have multi-hop networks, it lets us have some kind of radius and simulate an approximation of what happens in the real world. All right, usually I have time for 2 or 3 questions, but they're done. So let's get you guys to line up. And let's go through them. What's your number do you have?
65.
65.
65. 65. 65. 65.
65. 65.
So not only do they all have the same answer, they all have the correct answer, which is fantastic. Nice job, everyone. You can set the calculator down over there. I must admit, I'm a little surprised. Usually, middle school students just nail it. They're fantastic. High school students do a pretty good job, but not this good. College students, they struggle a little bit. Professional engineers almost never get it right. They screw it up, they ask for the cars back again, they lose calculators, it's terrible. So excellent job, you guys. You guys are performing at middle school level, which is very impressive. So here's the answer. How do they all end up with 65? It's explained very clearly right here. It's obvious. All right, here's a better explanation. So here are the numbers they all started with. And let's focus initially on number 10. So number 10 is the lowest number out there. No matter what number 10 averages with, of all the numbers, it will never be as low as 10 again. It will always get bigger. So 10, and in this case 10 averages 30, and they both ended up at 20. So now the lowest number is now 20. Likewise for 120, no matter what 120 averages with, it's going to get smaller. So if you imagine just the biggest numbers, after enough time of averaging, the two, the biggest and the smallest, the extremes, always get a little closer together. If the extremes are always getting a little close together, at some point in time, they're going to have to squish all the numbers in between them, and they're all going to have to be squished down to the same number. For the mathematicians out here, what's going on is that each local average reduces the global variance by a small degree. So if two numbers are not the same, there's some variance between them. When the two numbers are not average, they're the same number, that their local variance is down to 0. And the global variance is reduced by some small finite amount as well. And you can do a whole bunch of really scary math to show how the variance is reduced and what makes the network converge. There's a very deep, rich, a very beautiful theory on graph Faucians, and this is called agreement algorithms. Really cool stuff. I understand the key papers of this. I understand like a third of that paper. It's a scary paper. But it works really, really well. All right, so but it does beg the question, though. Why would you compute an average using this goofy technique? Why not just add all the numbers up and divide by 8? But what if you don't have calculators handy? What if you don't know how many robots there are in your network? Maybe your network is very big, and you can only see a very small portion of it. What if you don't know what a number is at all? What if you are a honeybee? So honeybees share food, ants and bees share food all the time with their nest bees. So if I have some food, and I find another worker who's hungry,